turn round if you've turned up a bit late. One of them is some handwritten notes on operation amplifiers to go with the lecture slides. One is last year's exam, and the other is my explanation of last year's exam, which is different to the solutions. That is not to say that the answers are different, the answers are the same, but the explanation says why the answers are the way they are, which is much more useful than just giving the answers. If you want the handwritten answers, you can download them off the website, which by now I hope you're all familiar with. Anybody not been on the teaching resources? Very well done for not saying so. So what I want to do with this lecture, and if necessary the next one as well, but hopefully not, is just to go through last year's exam to make sure that it's well oiled. Because the exams do tend to be quite similar. That is not to say it is a copy. And if you learn this exam, you will not do very well on the current exam. But the concepts that are involved are the same. So if you understand the concepts, then you will be alright. I'd quite like to start with question 6 because it's the offhand question. You may read into that, the questions always take the same order, if you wish. And it's the one that we've been doing most recently, so it should be at the top of your stack, or FIFO if you prefer. So the questions are up on the board at the minute, and question 6 part A part I says, draw the circuit symbol for an operation amplifier and label the inverting input, the non-inverting input and the output. You will not believe how many people thought I wanted something more. All it has to be is a diagram of an op-amp. So this is all that's required for 6AIA. Oh no, 6AI is label the inverter, so this is going to be inverting. This will be non-inverting. And output. Well, that's not pro, it's P. So 3 free marks. Lots of people drew me a non-inverting amplifier, an inverting amplifier, and then started labelling them up. Which wasn't what was required, it was just that. So that's nice and easy. That's the getting marks right in your own name bit, pretty much. Then I said, give typical values for the input impedance, output impedance, and open loop gain. And this tripped up almost everybody. You just have to learn them, they're on the lecture slides. And I can't even remember the numbers I give on the lecture slides, but input impedance is about 1 gigaohm, output impedance is about 50 ohms to 100 ohms, and open loop gain is anything from 10,000 up to a few million will be fine, or even 10 million. So there's a big range you can pick in, and it doesn't really matter what numbers you come up with as long as they're right order of magnitude. So you just have to remember them. So you're going to mark each for that, so it's 6 marks. There are 3 sets of notes. One is notes on, they're not here, they've already gone out. One is on op-amps, one is on the exam, and one is the answers to the exam. Make sure you take all of them. I don't know where it is, you're an engineer, you work it out. Right. State the op-amp equation and define the terms. So the op-amp equation is?
VO equals AV multiplied by V multiplied by V minus.
Yes. So for 2 marks, oh, and define the terms. One for the equation, one for writing out what it all means. So VR is equal to AV, V plus minus V minus, and this is going to be output. This is open loop gain. This is non-inverting input, and this is inverting input. I take it you're all looking at the paper, right?
Yeah.
Ah, then I'll leave this. I can leave the screen up, yeah? Good, that'll make it really difficult for people looking at the video. So it's a mark for the equation and a mark for the labels. And then we get on to the real questions. Identify the op-amp circuit in figure 6A. So this is 6 part B part I. And it's, well, which is it? Inverting? Although against inverting, I'm afraid you weren't right this time. It is inverting. And the next, so you get a mark for knowing that it's inverting. So then the next bit says find an expression for V out over V in, assuming AV is infinite. So this is the analysis that we did in the prior lecture. And what's the first thing you do? Sum the currents in the input node. If you flip to, I'm not doing it because we'll never get through the exam otherwise, but if you go into see, I'm now the master of the slidey thing. Oh, 6 is a long way away. Here we go. So yeah, you sum the equation 30. You sum the currents at the input node, and you say if you draw any arrows the way that I drew them. Okay, I didn't draw any arrows, but you can work out from the equation which way I thought the arrows were going in my head when I drew the diagram. And then you substitute in the voltages and yep.
So would you not get the mark if you just get the final equation?
Hang on, let me see how many marks there are.
3.
3 marks? No. You get 1 mark for the right answer, but I have to know what you're thinking, which unfortunately for me requires a lot of therapy afterwards. But yeah, you've got to actually show the method, because otherwise you could memorise a few key results and come out with a middling score. So yeah, if you want all the marks, it has to be derived. If I said state, if the question was not find or derive or show that or hence or otherwise, blah, 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 blah. If it was just state whatever I want to see, it would be for a single mark and you could state it without any qualification, and as long as it was right, you get it. So yeah, for this one, you can either read the keywords or look at the number of marks available, but for this one it has to be derived. The same goes for the next one. So yeah, you sub in the voltages and the resistances and equate it all to 0, so essentially 31, you've subbed in V and R into 30, and then you do some maths, and you end up with minus RF over RN. And the maths is your own business pretty much. So you get 3 marks. Now I wouldn't be giving out a mark for every line. It's a mark for the first bit that says you sum the currents because that's conceptual, a mark for knowing you sub in the voltages because that's the use of Ohm's law, and a mark for the right answer. There's three handouts that are going around. Collect them at some point. So that's how the marks are given out there. And then the next bit says show that V out over V in is equal to all that stuff if AV is infinite. And this is, obviously it shows that, so you have to derive it, but it's only really a partial derivation, because if you did the first bit of II, okay, that's to say you sum the currents and you replace the currents with voltages, you just carry on from that point. So you're most of the way there already, really. The rest of it's just maths and knowing what to do with AV. So what is the difference then? I sum the currents, I replace them with the voltages, I've got an equation that says V out minus V minus over R in over RF plus V in minus V minus over R in equals 0. If I was going for AV is infinite, what would happen next? If I was at this point here, I'd say V minus is 0. That's the important thing, because of all the spiel in this text here. It says that V plus is connect to the Earth, and because the gain is infinite, it's a good virtual Earth, so V minus equals V plus, therefore V minus is at 0 as well, so sub in 0, which is what it says when I said because, blah blah blah, that's what I'm saying. So you put 0 in here. On the other hand, for the AV is not infinite, when you get to this point, so 38 and 32 are principally the same equation, except you can't say this is 0 and that's 0. You have to leave them and rearrange 38 to get 40, which is V minus equals stuff. And once you've got there, you'd sub 40 and 0 into 41, which will yield 42, and then you rearrange it. No, you don't. Yeah, you slightly rearrange it to get 43, and this is where most people stop, because then they sit there and their brain melts while they try and work out what I did to make it look like it is on paper. All you do is divide through by AV. So AV goes away from the top, and you're left with minus RF, and then you've got brackets around this lot, 1 over AV plus RI, which is what I've got there. And that's how you find it in a textbook. If you get to this point, you'll get all the marks, but this is just for showing off sake, or vanity if you prefer. So they are the questions which are they are similar in nature to the easier tutorial sheet questions, and they are the ones that make up the bulk of the exam. The other bits are a bit harder. There is very, very little on the exam where I just throw something in there just to see, which is in the course but not really, never really mentioned it much, just to see what happens. There's usually one tiny little mark right at the end, just to separate the people who are really thinking from the people who are just learning. But most of the exam is stuff that you've already practiced somewhere if you've done all the material that I've given out. So part C is a multiple input op-amp circuit. And the question here is all about figuring out what you need to do to your resistor R4 to make the output 0 volts, given some inputs. So most of the question is specified, and all you have to do is find what R4 is. Students really hate these kind of questions because I never realised it, but when you push someone into a question halfway through, it's harder for them than just starting in the beginning. So it could be different this year, but it might not be. So to find R4, the method is that you have to use superposition to come up with the output voltage in terms of all the inputs, and then you'll have an equation which has got R4 in it, and you have to set something to 0 and solve it for R4, and that will give you a value. And because I don't believe very much in difficult numbers, you ought to find that most answers have nearly round numbers outcome from them. So if you ended up with 512 ohms, you can take that as I'm having a joke, because it's a power of 2. Just so you know you've got the right answer, because I don't want to have to penalise you for not getting the maths right. It's the understanding that I'm interested in. So V out due to V3 turns out to be 45, and all that's happened here is I've said it's a non-inverting amplifier, so V1 and V2 are not included. Consequently, they are switched off. They're voltage sources, remember, and since they're switched off, they are replaced by their internal impedance, and their internal impedance will be 0 ohms because they're voltage sources. And since they're replaced by their internal impedance, which is 0 ohms, they are connected to ground. So, if I had this circuit, well, that's wrong, try again. R3,
Yeah.
and there's V3, and then we got one up here, and one up here, and this was V1 and that was V2. So both of these are hooked to ground, So, oh, I've missed a resistor, haven't I? I could rejig this into, oh, nearly. I can rejig that into maybe we should buy shares in chalk. I'm getting through it today. And there's this up here. So this is R4, that's R3, that's what do I call it, R5 as feedback, was it? Yeah. And this will be R1 and that will be R2. So this now looks like a non-inverting amplifier with a potential divider on the front. So you can treat the amplifier and the potential divider separately. So you can say, oh, I'll call this V3 and I'll call that V+. But I know there's a really big impedance looking in there because we've said the gain's infinite. Did we say the gain was infinite? Yeah, we did. For all these sort of multiple input questions, it would be a bit too mean to make you figure it out with the gain that's not infinite. So even if it isn't written there, you can assume it quite safely. So we can treat the potential divider and the op-amp separately. So we can work out what the gain is for the op-amp, and we get 1 plus R5 over these two in parallel. Yeah? No. Maybe. You see where that came from? It's buggery. It's 45. If you don't like doing one big one plus a fraction, you can do it as the bit to ground plus the feedback over the bit to ground. But if you were to divide through, by the R5 at this point, you'd get the other form. So there are two ways of doing it. And, well, it's the same equation, you're just dividing through by one of the terms. And sometimes you'll see it in a textbook written out slightly differently, but it's all the same. So we've got the op-amp bit, which is that bit there, and then we've got the potential divider, which is that bit there, and you just multiply them together. And the reason you're allowed to do that is because the impedance looking in here is really, really big compared to the impedance looking back that way. If it turned out that this was a megaohm, and that was, say, 10 megaohms, we'd have a 1 to 11, a 1 to 9 divider. And if this was only a megaohm looking in here, well, that's a megaohm, that's a megaohm. So looking from this point that way, we'd see half a megaohm. These two in parallel with each other, and you divide them, it'd be all shot. So you've got to be a bit careful about the impedances when you're connecting circuits together and assuming that they don't interact. Sometimes they will. Luckily, if the circuit will interact, I would have told you so. And there is none of that here. But it will come later. So at the moment we can just take this and that separately, not worry, and we'll get 45. And then we can do the same for V out as a function of V2. And if we go back over to this one, get rid of that. We've now got a ground V3 because we're worried about V2. We'll ground V1 and we'll drive V2. Now, that's ground and that's ground, so what's that? Ground. There can be, there. That's ground, that's ground, that's ground. There is no potential involved anywhere. This is high impedance. No current will flow out this node, that way or that way. So if this is ground, then this must be ground as well, because this is now just inverting amplifier. So all this stuff goes away. to leave you with an inverting amplifier with an extra resistor, but since this is ground, this point's ground anyway, so this resistor has both ends at ground, so it goes away too. And it all boils down to a regular inverting amplifier, which is why you've got minus R5 over RT. And you don't have to derive these results unless you need to. You can just state them because that's not what the question's about. So that was 46. And then 47 follows by the same mechanism. It's instead of rubbing out R1, you rub out R2 for all the same reasons. And then you just say that 0 is equal to all the stuff you've calculated. And the reason you do that is the question asks, what's R4 have to be to give you a DC value of 0? So that's where the 0 comes from there. If I said, what do you have to do to make it 5, you'd have to set everything equal to 5. So then to get 49, you just sub in 45 through 47 into 48, and it drops out as that lot, which is a bit messy. But with a little bit of rearranging, no electronics, just maths, it drops into R4 is just a shade above a kiloohm. And if you sat in the exam and you thought, it's bound to be a round number, you'd be quite happy at that point, I hope. It's actually very difficult to write the questions to get exactly a good number. You have to be quite careful with the way you do it. But I think that's... Oh, there's another bit as well, yeah. So if you've got that far, which is... It seems like a lot of work for 5 marks, but the only thing that's getting tested there is whether you understand what to do with all the multiple inputs. The actual equations were tested previously, which you got marks for in Part B. Obviously, if you couldn't do Part B, Part C is going to present a lot of problems, which is why Part A is the easiest bit and Part C is the hardest bit. So, Part C, Part 2, or II, assuming R4 is a kiloohm, so get out of jail free card, find the output voltage, amplitude and phase due to the AC input. With these problems, you can worry about the AC and the DC separately for the same reason that you can switch off voltages if you need to and use superposition. So you can do superposition of different voltage sources and you can do superposition of AC and DC components. And if that makes you feel a bit sick, think about this. If I had a voltage source like this, which was, say, I don't know, 4 sine omega t, oops, plus phi, plus 10. You'd be happy with that, yeah? So there's a DC offset of 10 and a sine wave component of magnitude 4, frequency omega, and phase shift phi. What then if I said, alright, we have a sine wave and a battery, all connected to ground, and this is 4 sine omega t plus phi, and this was, what did I say, 10? 10 volts. Would you measure the same thing across the whole lot as you did before? Well, there it is, superposition. Because these are voltage sources, and I can switch either of them off if I want to. And if I did, what would I replace it with? So if I turn off this bit, I have 0 ohms there, which would yield the 10 volts is gone, you're just left with that. But you still have a good current return into your source because this is just a wire with a label. And you can switch off this one and leave yourself with just the DC. So you can do the superposition of the components just by saying all the components are secretly separate. There's no magic involved. Right then. Yes, so what do you have to do? Well, you work out what the gain is at V3 due to the output due to V3. and then you use the 5 sine bit, because the DC offset's half and the AC bit's 5, and you just plug it into the equation and out pops a number. And the number is 4.470 apparently. So the plugging in goes into 51, where most of 51 has actually come from 45, except instead of half, which is the DC bit, we're now putting in the AC bit. And the only other thing it says is, what about the phase shift? Because this is non-inverting, there is no phase shift. So whatever phase it went in with, comes out with. If it was inverting, whatever phase it went in with would come out 180 degrees shifted, or flipped if you prefer. Same thing. So that's the op-amp question. And they always follow broadly the same sort of structure. Some easy stuff, some derived stuff from lectures, and an applied question at the end. Let's go on to question 1. Any questions about that question? Good. Good. So this was the diode question. And there's a circuit with 3 resistors, a and 2 sources and a diode. And this is the usual sort of strength question. Actually, this question's got a secret trick in it, where you can collect 2 of the resistors together. If you've been reading your circuit theory, you'll know that R1 and R3 can be collected up, because you can move R3 to the other side of V1 without actually changing the mathematics of the circuit. If you figured that out in the exam, I'd be looking up who you were and deciding if I wanted to give you a PhD or not in a few years' time. I don't do that sort of thing very often though. So the first thing you have to do is figure out whether it's conducting or not. What's the first thing you have to do? Assume it's not conducting. I like it when everybody does that, because it means all the answer books look the same, in principle. If somebody says, right, I'm going to assume it's conducting and then show that it is, that's just frustrating, because then I have to work it out differently. And it takes me 25 minutes to mark the paper instead of 10. Please assume it's not conducting. It's a good idea though, because if you approach all of these diode questions the same way, you'll get the rhythm of it will get into your head, and then you'll just go in there and it'll be on automatic. If you suddenly decide, oh, I think this question might be a bit easier if I did it this way, maybe it's a trick, there really isn't. Always do them the same way, and that way you'll always be on method. So, if the diode is conducting, find the forward conduction current through the diode. However, if the diode is reverse biased, find the reverse voltage across the diode. I got complained at by our internal review process for making it a bit too ambiguous, so this year, this bit is labelled slightly differently, and it's easier to know what's going on. So what do you have to do first of all? Well, the usual method would be superposition, which is what I intend to do, but if you want to do this by loop analysis, that's fine, and if you prefer to do it by nodal analysis, that's fine as well. Although doing it by nodal analysis is not obvious how you would proceed, because the current source makes it a bit tricky. Nevertheless, it is possible. But we'll do it by superposition. So, we've got resistor, current source, diode, resistor, that it? What's the resistors?
1K, 2K.
Did I give them labels?
Oh, R1, R2.
Cheers. I'm not actually going to solve it, we'll just do all the partial circuits, because the maths I'm not too bothered about. So this is what it looks like, and you'd have to start by saying, I'm going to turn off all the sources one after the other, work out the circuits, and then spooge them all together to get the answer. So which one do you want to turn off first? Righto. Ah, there it is. So if I turn off the current source, what will I replace it with? Yes. So then there are no biscuits, I didn't buy any. There's not enough time for biscuits in this lecture anyway. So we'd have... Which one do you want to turn off next? Since I've drawn that already. Or which one, sorry, are we considering it or turning it off?
Turning it off.
Turn it off, well then we have to turn off another one as well. You have to consider one only and turn off the others. Since there's three, we need to choose another. So we turn off the current source. Which other one do you want to get rid of?
The diode.
Diode. So you want to start with V1 then. Is it V1?
Yeah.
So we'll start with V1. So our partial circuit will look like this. Where this is R1, this is R3, that's R2. So the diode's gone and there's a 0 ohm resistance in its place, because the diode in all this is either that, 0.7, or if you prefer you can make it a battery, it doesn't really matter, or it's that. There are two options for diode. There is no need to include the little resistance that lives in here, because we're not worried about small signals. We're only worried about whether it conducts or not. So current source is gone, replaced with internal impedance, which is infinite. Diode's gone, or the voltage source which represents the diode is gone, and replaced with its internal impedance, which is 0. So then we work out this circuit, given the value of R1, and what we're interested in is the diode current. Now, just by looking at it, I know that the current's going that way, because this is positive and that's negative, and the current wants to go that way. Everybody happy with that? Yeah, good. This is the diode, so the current's going that way. I have to keep my eye on that, because later on I might get one that goes the other way, and then I have to remember to put a minus sign in the appropriate place. So, can we agree these three are in series? So then, I's V upon the sum of R1 through R3?
Yeah.
Cool, done. I'm not going to bother writing it out, no point. So we've done this one, now we've got to do either this one or this one and get rid of the rest. Which do you prefer? Come on, it's a straight choice. No answers are wrong. What? Okay, we want to do the current source next, right? So to do the current source, we'll have to switch off the voltage source and the diode. So we'll have no voltage source, replace with internal impedance, which is 0. Resistor, R1. It's neutral. Coming in. Current source. It is that way, isn't it? Yeah. No diode, replaced with internal impedance, which is 0. So we'll end up with this. So, and the diode current is that one there. That's the one we'll have to work out for. So, could we agree that, sorry I didn't label that, that's R3, that's R2. So these two are in series, yeah? Happy with that? And then the sum of these two and that are all in parallel with each other. If you go back to the, so it all boils down to, God damn it, coming up. It all boils down to this. Which is if you go back to lecture 2 or 3 or whenever it was, it's a current sharing circuit, and the diode current will be that one there. So if you prefer, you can just draw it as that one there, which is the same thing, makes no difference. In which case, you know how much current, you know what the parallel of these two is, and it's shared out according to the lowest resistance get the biggest current. And then it's just the same as a GCSE maths question in which Eric and James are sharing apples and so on and so on. If you didn't do GCSEs, then you missed out on a lot of fun questions. How many apples does so-and-so get? How many? So it's the same thing. It's the opposite way around from sharing out voltages in potential dividers. Happy with that? So then there's. So we will work out well, I won't, but you would work out these answers and keep them. So we've worked out 2 answers so far, and now we have to worry about the diode because that's the only thing that's left to deal with. So to do the diode, we'd switch off the voltage source, and we'd switch off the current source, and we'd have 0.7 volts there. And this would be R2, that'd be R3, this would be R1, yeah. So now we've got another series circuit with a battery in it. Have I made a mistake? Oh no. Alright, right. So I thought you'd noticed something. So we've got, and the current we'll be looking at now is that one. And that's why the direction of the current is important. In the very first circuit I had, we drew the current the other way. And we'd have to make sure that we subtracted this one from the first one. Or subtracted the first one from this one, depending on how you want to write your equations out. One way or the other, they can't both be added. So we do R3 plus R1 plus R2, 0.7 divided by that lot, gives you the current. And then you'd, taking the signs into account based on the directions of your arrows, add them all up. Where did we get to? There we go. So the adding up is equation A. Now, I knew this diode was conducting because I wrote the question. You will not have known the diode is conducting. So before you do this bit of analysis, you have to do the bit of analysis that says, I assume the diode is not conducting. I just stepped in and solved it. The reason is it's nearly 11:15 and we've got to get on it. So if you aren't happy with the diode not conducting bit, It's the same drawing out of circuits. The only thing is, you'll have to say what's the voltage between the anode and cathode and show that it's more than 0.7. Then you step into where I took off. The full solution is given out in the handout. So, part B asks, what does part B ask? Now, if the current source is replaced by a variable current source, what will the current be that causes the diode to be on the point of conduction? Alright, what's on the point of conduction?
It's not 0.7 volts across it, but there's no current line.
Yes. 0.7 volts across it, anode greater than cathode, with no current flowing. So what you must do then is say, I will draw out a circuit where there is 0.7 volts across that diode, and I've already said there's no current, so no current will be one of your constraints, and you work back to find the value of I1. I fear I will be lecturing tomorrow. Pity. So where are we? Part B, yeah. So in part A there were 3 separate calculations for the conduction, and they were done with superposition. And 2 of them haven't changed. So ID due to V1 and ID due to VD has not changed, they are the same. So you can use those answers directly. Only thing that's changing is I1, because the only thing we've made variable. So we know the diode current will be 0 amps, and we know that I1 will be used to cancel the current that flows due to the other 2. So I've got 3 partial circuits, or 3 superpositions, 2 of which I'm not in control of, and they will cause a current to flow. And that current will be 1.25 milliamps plus minus 0.175 milliamps, because this is ID due to V1, and this is ID due to VD. This is the one that I'm now in control of. So the current that has to cancel is, ID to cancel is ID V1 plus ID VD. So you subtract one from the other because their signs are opposite. And if you had an ID I1 of 1.075 milliamps, that would make equation 8 equal to 0. And that's all you're attempting to achieve. You're allowed to adjust one of the superposition circuits to make the sum of all n of them, in this case 3, 0. Where are we? We've got a little bit of time left. Are you happy with that, or do you want to hear it again? 1 happy. 2 happy. Right, okay. This is rather old stuff now. You might have to go back and do some of the questions. But this will guide you through the method. So if you do this question, you'll be able to check it along the way. There is, however, another method, which a student put in their paper last year, which I was very pleased about. Essentially, they realised they could move R3 up to R1, and that makes everything a lot simpler in terms of writing out the maths. So it's much shorter answer than what I gave. The next bit of the question is about the 5 circuits. And the question asks, briefly describe the operation of the circuit in figure 1b, assuming the time constant R1 times C1 is much greater than the period of the input signal. So this is our sort of November through Christmas type stuff. What is that circuit? Of which kind? Positive, negative? Positive. Positive. So, if I had briefly describe the operation, what I'm asking is, tell me how the capacitor is charged and discharged over the course of a couple of cycles. You have to talk about the diode current and the capacitor current, and you have to say how the capacitor is replenished with charge and how it is discharged. If you don't mention those things, and obviously say something that's logical and correct, you can't obtain any marks. So my model answer for this is well, it's more or less what I've written in that paragraph that's on the screen now. The input voltage V1 is sinusoidal and centered on 0, and the output voltage Vout is taken to R1, and the minimum is minus 0.7. When the input tries to fall below minus 0.7 volts, then the diode conducts and the charge moves onto the right plate C1, blah, 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 blah. And you have to just go along like that. Imagine you were writing out algebra, but like Al-Kindi, you hadn't worked out algebra could be written with letters, or that 0 exists, but that's a different story altogether. And you write out everything in words. So the unknown quantity is 1/2 times the known stationary quantity times, and you write out all your algebra in words. That's how it was done for like a couple hundred years in the middle of the period of great Islamic science. But we have to do it in words for circuits now. And if you can't write something coherent, you're in trouble. It doesn't have to be in prose, you can write bullet points, that's fine, as long as it's logically ordered. So you can't start in the middle, then jump to the end, and then go back to the beginning, because you have to show that it's causal. That's to say, a voltage appears, a current flows, that involves charging up, then the voltage goes away, and then there's discharge. You can't mix up the order of things. But anything that's got enough key points to get you the marks will get you all the marks. So it doesn't have to be totally perfect, because you could write 9 or 10 different bullet points, but there's only 5 marks available. So as long as you write 5 sensible things, which are all true, and broadly follow the right order, you'll definitely get all the marks. And then the next bit says, sketch on labelled axis the input voltage VI and the output voltage VO and the capacitor current IC. Right. Either you learn how the circuit works and work it out, perfect, or you learn all the diagrams in the notes and reproduce them verbatim like a photocopier. Equally impressive, I feel, but not nearly as desirable. And the answer for this one is that one there. And then the next bit of the question says, I've squeezed my peak detector together, my voltage clamp together with a peak detector, and I've produced a peak-to-peak detector. Please draw the circuit, and it's 14, where C1 and DCL are the clamp, and DPK and C2 are the peak detector, and R1 is the load. And then the next bit of the question says, draw me a few cycles, and I don't think I asked for everything that's on this graph, but this graph dropped out of the lecture notes and I couldn't be bothered to produce a different one. So the question actually asks, assuming the peak-to-peak detector is sinusoidal input, sketch on separate labelled axes the peak detector input voltage and peak detector output voltage and the capacitor current. Okay. So I have actually asked for most of that. The only thing I haven't asked for is the diode currents. So the yellow and green aren't necessary. All the rest desirable. Yep.
Would we get graph paper in the exam?
Nope.
Okay.
Just sketch. There's no need to. Yeah, it doesn't have to be. I'm not asking for a spy simulation. It has to be sufficient that I can look at it and go, yeah, they know what they're doing. A good trick is when you start drawing your sine waves, because usually you draw your input first. Wherever it crosses the axis, or wherever there's a top bit, a turning point, put a little vertical line, because then you'll be able to line up stuff. Otherwise, if you, over the course of a couple of cycles, very easy to make time drift. And that's when I have to start drawing little things like that to decide if I believe or not. And it's obviously that takes me a bit longer than just looking at it and go, yep. Ideally, you'd all either write nothing on your paper at all, or you'd all write perfect answers, because they're both minima for my marking time. Obviously, I don't really want the first one. Right, we're more or less at the end of question 1, although it was a little rushed, and we are out of time. So we will do the transistor question tomorrow, and I may even have a demo for you.